Thank you very much for the introductions, and thank you for coming to this seminar. I will try to show the overview of my research in last several years about spontaneous motion of droplets and a particle. So the motivation of my research is to understand complicated systems such as cell motility and cell mechanics in a simple physical or mathematical point of view. It is of course very difficult problem, but these are, I think, two very encouraging experimental results. One is cell, which doesn't move in a circular shape, but after changing shape slightly, its cell starts to move in one direction. And in addition to that, the really important thing in this system is that this cell is not real cell in the sense that this is a fragment of cell. So therefore, many proteins are missing in this cell, but even though it can move, as the original cell does. The another movie shows much simpler experimental result, which is alcohol droplet on the water, and due to the evaporation of alcohol on the water surface, coupled with motion and the deformation, so this droplet, the black one, starts to move and deform spontaneously. Of course, these two systems are completely different in the length scale and the time scale, but I think there are two very important issues in these systems. One is both systems are not being pushed or not being pulled. So there's no external mechanical force acting on the system, but even though they move spontaneously. The other thing is that by breaking the symmetry, these droplet and the cell choose one direction and starts to move. These are something I'd like to discuss in this talk. And for the first part, for force-free motion, as we have seen in this could be seen in a very classical example. For instance, pholetic phenomena. So electrophoresis is a particle motion under electric field, and diffusiophoresis is a particle motion under concentration gradient. And under temperature gradient, this is called thermophoresis, or some people call solar effect. And here is the movie of thermophoresis. So bright spots are particles, and escaping from laser spot. At the center, there is a laser spot, and therefore temperature is higher here. So particles are escaping from the hotter place. Another example is what is called Malangani effect, which is the motion of the droplet or bubble and the surface tension gradient. And this surface tension gradient is driven by temperature gradient or concentration gradient or something like that. So important thing is that, as I have mentioned, there is no force acting on the system. Therefore, if you integrated stress tensor over the surface of the droplet, there is no this force should be zero. And so let me show some concrete example for the Malangani effect. So suppose there is a temperature gradient. Here is higher temperature, here is lower temperature, and here is a droplet, and typically surface tension is lower here and higher here. And therefore, this surface tension gradient creates tangential force, which also creates flow inside and outside the droplet, and this flow leads to the motion of the droplet in this direction. And the velocity of the droplet is calculated as the velocity is proportional to this gamma 1, which is essentially the gradient of temperature or concentration, whatever. And the proportional constant is dependent on the viscosity inside and outside the droplet. And this velocity is, in order to get this velocity, we actually need the condition of force free. And also what you could see from here is that this droplet is not being pushed or not being pulled, it's just swimming in the fluid. So, well, let me show the one example of the difference between force motion and force-free motion. So here's a I show the velocity field around the droplets under force motion. So as you know, the velocity decay is 1 over r, while in the force-free case, velocity decay is 1 over r cubed, which means that the velocity decay is much, much faster. This is because this 1 over r term is essentially from Stokes' let, which is proportional to the external force. So therefore, in the force-free case, this term disappears, and therefore this 1 over r cubed becomes the dominant term in the velocity field when it moves in one direction. And in this talk, I will talk about the several types of spontaneous motion. The first example is, as we have seen, the motion under the external field, though there is no mechanical force acting on the droplets. So the second example is that the field, the external field is uniform or isotropic, but so particle, if the particle has some asymmetry, then particle could move spontaneously. And these two systems could be reasonably described by linear theory because the symmetry is already broken. So therefore, we could do some linear theory for that. And it's reasonably described the experimental result, for instance. But on the other hand, the last two examples are not described by linear theory because so these are, the question is, how could we get the spontaneous motion in isotropic system? And by breaking the symmetry. And I think there are two ways to break the symmetry, either in bulk or the motion itself, break the symmetry and choose in one direction. So I will show this system in details. And here are some experimental results of spontaneous motion in the isotropic system. So here, the oil droplet is moving in water, and they are moving spontaneously. So this system is originally isotropic, but it's still the droplet choose one direction and it moves like this. And what is different? The point in this experiment is that they use some special surfactant which has chemical reaction. And first, surfactant dissolved in water comes to the interface between oil and water. And after some characteristic time scale, the surfactant decomposes into the head part and tail part and loses its function. And therefore, it's sort of a chemical reaction. And this chemical reaction drives this spontaneous motion. This movie shows the wave inside the droplet. So this droplet contains the nonlinear chemical reaction, which is Velozov-Jabotinsky reaction. So it's hard to see, but these waves, the red part is here is a wavefront, and depending on the position of wave, this droplet is moves and back. and not only translational motion but also rotational motion is possible. So here's another very simple experiment, I think. The oil droplet on the water, and they put some solid soap at a particular point of the droplet, and then they measure this kind of rotational motion. We did some theory for that, and I would say the rotation is more difficult than translational motion, in the sense that since we are discussing the motion driven by surface tension gradient, and because of this is gradient of some scalar, which doesn't create rotational flow, so we need some trick. So I won't discuss this rotational motion in detail in this talk, but still I think this is very interesting topic. And as for patterns in droplet or in cell, so you could see inside the cell, we could see this kind of patterns or waves, and which seems to correlate with motion and the deformation of the droplet. So these are things, something I really want to understand, but we are quite a bit far from that, but we are now trying to understand this kind of, these are final goals of our research. So let me start from the motion and the given external gradient. So here's crystallization of colloids under temperature gradient. So maybe laser spot is somewhere here. So therefore temperature is higher here. So there is temperature gradient, larger temperature gradient from here. And the colloid particles are driven by two fluxes. So one is diffusive flux, which is proportional to gradient of colloid concentration. And also, this colloid moves depending on the temperature gradient. It has some pholetic motion. And the balance between two terms determines the steady state of distribution of colloid distribution. And when the motion of colloid, which is proportional to temperature gradient, is characterized by this dt, which is called the thermal diffusion constant. And when thermal diffusion constant is positive, the colloid moves toward colder place, and if dt is negative, colloid moves to the hotter place. So in this case, apparent dt is negative. But the interesting thing in this experiment is that actually dt, thermal diffusion constant for these bees is positive. So if we don't put PEG is neutral polymer, it's just polymer, and by increasing the concentration of PEG, you could see these brighter spots. These are colloids, and first colloids escape from the laser spot. It starts to accumulate at the center. This means that the thermal diffusion constant changes its sign. And the people in this field usually use Sode coefficient, which is dt over d, and therefore we have measured this Sode coefficient changing its sign. And yes, and if we quantify that, here is the concentration distribution of bees relative to this far away from the laser spot. So you could see that as you increase the polymer concentration, the colloid is more accumulated at center. So here's the Sole coefficient as a function of concentration of PEG. And this is something we want to understand. So apparent Sole coefficient has two contributions. One is Sole coefficient of B's, which is positive, and this changes sign by adding polymers. And we did some hydrodynamics for that. And here's just Stokes equation, because this is a very small system, and with some forcing term. And this forcing term is dependent on the concentration difference, the concentration field, delta C. And the delta C is concentration with respect to the reference state. And now reference state is not uniform distribution, but a linear gradient because of the we apply the temperature gradient. So polymer concentration is linearly dependent on the temperature distribution. And the important point is that the far away from this colloid, the pressure is constant. Well, the outside this particle, the pressure is constant. Well, this is because hydrostatic pressure is cancelled by the osmotic pressure, so like this. So therefore, this particle is not pushed by osmotic pressure, but it creates some flow around this colloidal particle. And just solving this Stokes equation, we could get the velocity of this particle, well, which is proportional to temperature gradient, and the size of this colloid. And also it's crucially dependent on the interaction between colloid and polymers. And we assume this interaction is idealized excluded volume interaction, which means that this interaction is characterized by the size of this polymer. So intuitive picture of this phenomena is that this free energy change during this the motion is balanced with some dissipation, and free energy change is proportional to this surface free energy change is proportional to the surface area, of course, and also the change of concentration at the surface of the colloid. You see the concentration of polymer actually, and this is balanced with dissipation, and usually people balance with Stokes drug dissipation, but this is not true in this case because dissipation occurs only inside this thin layer of interaction between colloid and the polymers. So therefore, the velocity gradient is u scales like u divided by this lambda length scale of interaction, and this is surface area. This is the area where dissipation occurs, and this gives the rough estimation of the velocity of the particle. And if you use the estimation like usual Stokes work, which means that u divided by size of particle and a cube, this gives some wrong answer. This is an important point. And if we compared with the experimental result, the apparent Sole coefficient is bare Sole coefficient, which is known, and minus some correction term, and this correction term is proportional to the size of colloid and with some characteristic length scale. And this STP determines the reference state of concentration of polymers, and the STP is essentially Sole coefficient of polymers for PEG. This is also known. So if we put the numbers, then we could fit experimental results quite without any fitting parameter. And using this thermoflashes, we could we could get some spontaneous motion even in isotropic field. So here is we use the Janus particle, which has which half coated by gold. This is silica beads, I think, and half coated by gold. If we shine the laser, when we shine the laser onto this particle, this gold part heated up, and here's the temperature distribution around the particle. So here is temperature is higher, slightly asymmetric, you see. So here temperature is higher here and lower here. And this temperature, local temperature gradient creates the motion of this particle. So this, what we call self-thermoflashes, is also analyzed by very simple hydrodynamics and coupled with heat equation. There is some appropriate boundary condition because by shining the laser, it's, the gold part is heated up, and therefore it creates some temperature gradient locally. And what is interesting is that the velocity is proportional to the temperature, local temperature gradient, and with some unknown fact, which is the interaction between this particle and some surrounding fluid. This is really difficult to measure. In the previous case, what we have used the polymers, then it is quite easy to measure such quantities. But in this case, it's a bit hard to measure. But we found that this unknown parameter is actually rated with Sode coefficient of this particle. And this Sode coefficient is, could be measured independently from this measurement by passive, how this particle behaves under the given linear temperature gradient. And we estimated the Sode coefficient in two ways, and well, they are not exactly the same, but the order of magnitude is quite reasonable. And what is difference between the passive Sode effect and this self-thermoflashes is that the particle has some polarity because it's half coated by another thing. So therefore, it has some direction, and therefore it has some rotational diffusion, and which creates some enhancement of diffusion constant. And here we could estimate how this enhancement. Actually, this enhancement is like this. This v is the velocity of the self-propulsion, and the tau r is a typical time for the rotational diffusion. And in our case, since we use the optical tweezer, eventually this particle is trapped by optical tweezer in the long time scale. So therefore, we need to add some spring potential due to the optical tweezers. But anyway, we could compare the mean square displacement. We could measure the effective diffusion constant, and since we know the rotation diffusion constant, we could compare it with the experimental result. So far we have discussed the motion under given broken symmetry, and from now I will try to discuss how we get the spontaneous motion in the isotropic system. So suppose there is a droplet in water. If the surfactant distributes isotropically at the interface between two fluids, then obviously there is no motion. So everything is isotropic. But if the surfactants accumulated at one side, then this surface tension here is lower and here is higher, which creates flow. and therefore this droplet moves in this direction. So the question is how this transition occurs. And this kind of idea is not necessarily confined in the using surfactants, but also we could think about some heating or some production of the chemicals inside, or some heating, or maybe other situations are possible. And so what we want to do is to derive the equation for the velocity of the droplet, which is something like, so eventually we could get this kind of form from reaction diffusion equation with some advective term. And this equation is now written in the droplet frame, so therefore this V contains two effects. One is convection, and the other is the fact that this droplet is moving. And these reaction diffusion equations coupled with the hydrodynamics. And if we want to think about the surfactant, we need to think about the surface separately. But for simplicity, today I will talk a more simpler situation. So, so let us consider the hydrodynamics. So hydrodynamic equation is written like this. So basically Stokes equation. Because we are interested in close to the critical point between the stationary state and the moving state. So therefore velocity of droplet is small enough. So to justify this Stokes equation. And here is what is called the Korteweg stress, which is written like this. And phi is the field. Phi is used to describe this droplet. So phi 1 shows there is droplet, and phi 0 is there is nothing. And the B is essentially surface tension. And so here is just assumption, but we assume B is proportional to, there is a linear relationship between B and the concentration of chemicals.
Excuse me, then the gradient of phi is proportional to the normal.
Which one? This one? Okay, this one is essentially gradient of the normal, yes.
No, it is the normal. The grad of phi is proportional to the normal.
Yes, if you grad phi is divided by absolute value of grad phi, this is just normal, yes. Yes. And so what is good for this formula is that if we take the sharp interface limit, then we come up with the conventional boundary value problem. This is just Stokes equation without any forcing term, but we need some appropriate boundary condition, which is called stress jump due to the surface tension. And also at the given, if this concentration distribution is given, then we could get this velocity of the droplet, which is exactly the same as we solved this conventional boundary value problem. And this the force term here could be described in this form. And this is essentially accumulated at the interface between the droplet and the surrounding flow. And this has two contributions. One is normal direction and the other is tangential direction. And this one is just Laplace force. And this one is capillary force, which is proportional to the surface tension gradient. So this is this creates this force creates a flow. And if we expand this surface tension into the Legendre polynomial and describe each mode, the amplitude of each mode gamma n, then the motion, the velocity field is described by the Osen tensor, as we have seen in the morning session. And here is the force term. Since we assume the surface tension is proportional to concentration of chemical, so here is the Laplace force, and the tangential force is also creates some velocity field. and we could calculate, once we know the velocity field, we could calculate the normal velocity at the interface, and from which we could calculate the velocity of the droplet, and so on, so on. And then finally we could get the form of the velocity of the droplet.
You still assume no slip on the boundary.
Boundary is continuous. The velocity, since this is droplet, velocity is continuous at the boundary. So yes, this is droplet. And close to the critical point of the drift bifurcation, we could expand the concentration distribution in the Fourier space, assuming that. Sorry, I didn't show the dynamical equation for the chemical concentration. So here is our dynamical equation for the chemical concentration. So it's just diffusion equation with some production of chemical. And the fact that this droplet is moving gives two contributions. One is here, since this production occurs only inside the droplet. So here is the position of droplet appears here. And also there is a convective contribution. So so in this talk I will neglect this convective contribution, but we could perturbatively include this term, but the result is qualitatively the same. It changes the critical point. The critical point shifts slightly, but essentially the same. And now we want to describe the shape of the droplet. So here we assume the small deformation, and they expand this the position at the interface in the spherical harmonics. And then we have this kind of kinematic condition which determines the shape of the shape of the droplet, because here is deformation, time derivative of deformation. So this equation is essentially the time evolution equation for the deformation, and it is convenient to introduce symmetric tracer tensor by multiplying many normal vector onto this deformation and the integral over the surface, and we could define any rank of tensors. We characterize the shape of the droplet, and we will see what the meaning of these tensors later. So since we know, so if the concentration distribution is given, since we know how much force acting on the interface between the droplet and the surrounding flow, we could calculate any moments of force. And since velocity field is expanded into the, this is just multiple expansion. This is F is Stokes sled. This is dipole, as we have seen in the previous talk, and quadrupole, and so on and so on. And in this case, also the Stokes sled is 0, as it should be, because this is system is force free. And actually, if this Stokes sled exists, the velocity field decays 1/r. So this is the standard hydrodynamics. And also we could calculate the higher moments, dipole, which is proportional to the second mode of surface tension, and the decay is 1/r squared. And quadrupole is proportional to gamma 1 and also gamma 3. So the thing is that this droplet, the motion of droplet is driven by this quadrupole contribution, which is proportional to 1/r cube. That's why we have 1/r cube contribution. for the velocity field in this motion. And this quadruple contribution was for the pholetic phenomena. This was pointed out by Frank Richer and Jack Paul explicitly. But this is the same story applies to the this Malangoni, the self-propulsion driven by Malangoni effect. And then this sign of gamma 2 is very important, and we want to call this negative gamma 2 is puller and the positive gamma 2 is pusher. And actually this dipole controls the deformation. So this is nothing to do with translation of motion, but determines the deformation of the droplet. So here I draw the a flow field outside this droplet. So when gamma 2 is positive, which means that this part has a higher surface tension and this part is smaller surface tension, and which creates the force something like this, and this creates a flow like this, which means that this droplet is pushing fluid. This is pusher. And the opposite case is that the flow is something like this, which means that this droplet is puller. And since in this case, since this part has higher surface tension, these parts should be flat compared with this part. So therefore, the shape should be like this. And in the opposite case, shape is something elongated towards the direction of motion. So, since we assume the linear relationship between surface tension and the concentration, all of them determines, which is the sign of gamma 2. So, and the shape of the droplet and the direction of flow field. The reason why I'm discussing about the sign of gamma 2, or whether this is pusher or puller, is that in the talk, in the previous talk, we have seen many examples that pusher and puller are quite different and significant meaning, and also there are some theoretical study and experimental study saying that the active suspension is really dependent on the sign of this gamma 2. Therefore, we are interested in the sign, or whether this our system, spontaneous motion driven by chemical reaction, is whether this is pusher or puller. This is something we would like to discuss. So these are expanding close to the critical point of between the stationary state and the moving state. Eventually, we could get this kind of coupled ODE, so up to the cubic order. So epsilon is essentially the velocity of the droplet. So we expand close to the critical point. And so here you could see that this is Landau type equation, but coupled with the second mode. And the second mode is described by some damping with coupled with translational motion. And third term is essentially slaved by these two modes, but described like this. And the meaning of this tensor is that the positive, if SZZ is positive, this deforms like this. If this SZZ is negative, it deforms like this. It determines the how to say this ellipsoid or poroid shape of the droplet. And the third band tensor determines the shape of something like this. And as for translational motion, so from this equation is clearly, it is very clear that if tau is smaller than 1, this term is negative, therefore stationary state is stable. But when tau is above 1, so it bifurcates and you have stationary finite value. There is no trivial solution for that. And this is a supercritical bifurcation. And we could calculate tau explicitly from the coefficient appeared in the original equation is a viscosity diffusion constant, and beta is some typical length scale determined by the ratio between diffusion constant and some damping thermal concentration field. And the gamma c is the coefficient of proportional constant between concentration and the surface tension. And A is strength of source. And this creates some non-dimensional number, which determines how the system away from the stationary state. And we could calculate the velocity explicitly, and like this. Here's deformation. And so, as I explained, we were interested in the shape of the droplets, what kind of shape it is when this droplet is moving. So sign is actually determined by lambda, this coupling constant of second mode with the velocity. And actually we found that this lambda is always negative, which means that gamma 2 is always positive, and which means that this droplet, the shape of the droplet is something like this, elongated, perpendicular to the direction of motion. And this is actually pusher. This is characterized by pusher. So, therefore, the conclusion of our calculation is that the spontaneous motion driven by this kind of chemical reaction is characterized by pusher. So like this, and yeah, I mean, in so few minutes, I'd like to show just few slides about the couple of internal nonlinear patterns and the motions. Here is the experimental result that that is the same as I showed in the introduction. So here is droplet motion. So couple with the laws of Jabotinsky reaction inside the droplet. So we did some similar theory, coupling with hydrodynamics with, so in this case, the internal pattern is described by some nonlinear reaction diffusion equation. And then we just solve this part numerically, and since we know what kind of flow occurs once the surface tension is determined, and then, so here's just, we could get this kind of motion coupled with the pattern inside the droplet. And here's the velocity field. And actually there are, in the experiment there are several patterns appear. So here's some rolling pattern. Here's also scrolling patterns. It's hard to see, but this axis symmetric rolling patterns. So always appears something like this. And we could reproduce numerically some like these patterns. So the conclusion is that we've shown several types of spontaneous motion and also deformation. But still, we have many things to do, I think. For instance, we are interested in interaction between droplets with arbitrary shape, and once we know the interaction, we may calculate the collective behavior of this kind of system. And also, we want to include the fluctuation, but which leads to the stochastic partial differential equation. But we are still not very sure how to deal with that. And what is the appropriate way to include the fluctuation? Also very important problem, I think. And what we have discussed is very simple droplet, but we want to include some complexity inside the droplet, for instance, liquid crystal or some viscoelasticity and so on and so on. And also in the first part, we described some hydrodynamic description for the thermophalaces, and we believe that this is correct when the size of colloid is large enough and the surrounding fluid is, just can be regarded as really fluid. Then this is okay. But if the size of colloid is comparable with, for instance, polymers surrounded by this colloid, then we need to think about the interaction between colloid and the surrounding molecules more explicitly. And the question is how to describe, such a microscopic state. This is still, I think, open question, and we want to understand how to describe whether it is possible to give some mesoscopic description for such kind of something in between microscopic and macroscopic system. And this is something I want to discuss further in this program. So thank you very much.
So you showed that these chemical dynamics produced moving particles that can be classified as pushers. Would you say that drops with chemical reactions cannot be pullers? Do you think that would be true?
I mean, okay. The quick answer is I don't know. I cannot say, in general situation we don't know what is happening, but what we could say so far is, for instance, this sign matters really dependent on the character of surface tension. And for instance, if you could create a system where the droplet deforms like this when surface tension is higher here and lower here, which is which looks very strange, of course, then you could get opposite sign. And this looks very strange, and this looks very unphysical, but as far as we calculated, if we include some surface, I mean, what we have discussed is just a droplet in bulk, but if we include the surface, then we found that this sign could be opposite. So in that case, I mean, this pusher-puller stuff could be opposite, but I'm not sure how general it is.
And you're saying surface, that's a no-slip surface?
No-slip surface, yes.
In your second system, the Belousov-Shogoshinsky reaction, you showed that the droplet moves as a result of the reaction. I mean, how is the reaction influenced by the motion? Do you see by coupling or?
Okay, there is coupling through the advective term. So here, there is this term.
Mm-hmm.
But unfortunately, in this system, nonlinear effect in bulk is too strong to kill everything with this bulk backboard interaction. So, so frankly speaking, this system is simpler than the spontaneous in the previous spontaneous motion of the droplet, because this non-linearity in bulk conquers everything, almost everything. So once we know the pattern in bulk, we know the motion and the flow, and this flow slightly affect on this chemical reaction, but the effect is very, very small. So in this system, at least. No questions?
Okay, we'll thank the speaker again.